Okay. Good morning, everybody. So this is the last lecture on inflation. So I want to round up a couple of things and today mainly talk about non-Gaussianity and then also a little bit about inflation in string theory and generally the problem about the UV sensitivity of inflation. So connecting it a little bit more to high energy physics. So here I'm summarizing what we talked about last time. And somebody just told me he has never seen this figure. This summarizes a lot of what we talked about in all the three lectures. So it shows the co-moving Hubble radius. This explains why the horizon problem is solved. Then if you look at a co-moving fluctuation mode, so its wavelength doesn't change with time. So it has this feature that it exits the horizon, then re-enters the horizon. And if we look at the correct variable, which is this co-moving curvature perturbation, then it has the convenient property that it doesn't evolve on superhorizon scales. So we have superhorizon scales here, subhorizon here. And what we did in the second lecture is compute this power spectrum quantum mechanically for this superhorizon, at horizon crossing for this curvature perturbation. And then last time we discussed how to relate that curvature perturbation to actual observables. And in particular, we talked about CMB temperature and polarization. And I didn't talk much about, and I might not get to it today, and it's not so important because I think other people talked about it. I didn't talk about galaxy surveys and large-scale structure. So you can do a similar relation between, so then here's a basic relation that goes from a co-moving curvature perturbation to an observable delta t or delta rho by using some explicit transfer function that we can compute. And the property is that it's some known physics that we're confident we understand. And so we can go back and basically solve the inverse problem and relate this to something at very, very early times. And so the additional steps that you have to do when you look at galaxies, for example, is that, okay, maybe I do say some things about it. So when you look at the sky and you look at galaxies, you see this. Basically what you measure is you measure the number density of galaxies within a certain volume, or the density contrast that is defined like this. And then you have to ask yourself how those relate to an underlying, because the major matter component in the universe, of course, is dark matter. And so you can also define a density contrast. So here, this is the density contrast for galaxies. This would be for dark matter. And it's, in fact, the dark matter that relates most directly to this curvature perturbation. So you can write down you can relate the power spectrum of dark matter at some late time and this to a transfer function. And then here there's the primordial power spectrum. So here's a transfer function here. This is just conventional. You factor out this factor of to the 4. And then some numerical coefficient that is historical. But in any case, and this is something you can compute. You can either compute it approximately using some analytical approximations of some fitting functions to numerical results. But this is something known, and so you can infer from, if you were able to, to measure the power spectrum of dark matter, you could directly relate this to the power spectrum of the initial curvature perturbations. The problem is typically we don't actually see the dark matter directly, with the exception of lensing maybe. So there needs to be one additional step to relate this to the power spectrum of galaxies that we actually see. And this is usually done by something called, you define a linear relation between the dark matter density and the dark matter density in galaxies. So this parameter here is called the bias parameter. And this is just something you have to infer from your measurements. So the way you infer this is you measure the 3-point function of galaxies rather than just the 2-point function. And the 3-point functions will depend in a different way on this bias parameter, and from that way you can somehow extract this. Okay, so those are the steps. You measure the power spectrum of galaxies. You relate this observationally to the power spectrum of dark matter. And then you use this. You compute the transfer function and therefore extract what the primordial power spectrum was like. Okay. But at the end of the day, the final answer, the final goal you have is you want to observationally constrain this function here. Yeah? So the power spectrum of primordial scalar fluctuations. Yeah? So most of our measurements, at the end of the day, boil down to some constraints on this primordial scalar fluctuations. So for example, last time, so if you multiply this by k cubed over 2 pi squared, there's some scale dependence, and we have constraints now on this scale dependence. Like this. And then something that I mentioned, and I just want to list here again, because I think it's important, is that there are two qualitative features of these scalar fluctuations. That are even more striking than this numerical result. This evidence for scale invariance. And that's the fact that you have coherent phases for the different Fourier modes. And that explains, why we see these acoustic peaks in the CMB. If it wasn't for these coherent phases, we would expect to see something that just looks like white noise and doesn't have that structure. Yeah? And for example, that's true for alternative mechanisms to produce these scalar fluctuations, like cosmic strings and defects. Typically, always predict a shape that looks something like this. Yeah? So really, this coherence of the phases, which really comes from the fact that these modes have exited and then re-entered the horizon, and they re-enter the horizon with a fixed, with r dot equals to 0, and that defines their initial phase. Yeah? So all of them have a synchronized phase that is determined by this super horizon freezing. Yeah? And so it's in some sense these coherent phases, are like an indirect evidence for the fact that you had this, exit and re-entry feature. And then this can actually be combined with the fact that you also observe them to be on super horizon scales. So for the temperature fluctuations, so here I'm plotting the angular power spectrum for temperature fluctuations. Yeah? For them, it's actually not that, these oscillations are actually happening on sub-horizon scales. Where by sub-horizon, I mean sub-horizon at the time when the CMB was released. Yeah? So you could imagine that you could cook up some causal theory that actually mimics this. And people have tried this in the 90s. Yeah? There's actually a way of trying to tune your defect model in such a way that it actually reproduces this inside the horizon perfectly. Yeah? It looks very ugly. It's not the nicest thing you can write down. But it's not logically impossible to do. Yeah? But then last time I also talked about polarization. And in particular, you have these two different modes of polarization, E modes and B modes. And so what WMAP did recently was they looked at the cross-correlation between temperature and this E mode polarization. So they plotted the CL, TE, yeah? And they found a spectrum that looked like this. Yeah? And so it's also mainly sourced by these scalar fluctuations. So measuring this, you can actually predict what this should look like, because it has the same primordial source, and you can compute the transfer functions. So you could actually, before even measuring this, you can make a prediction what this cross-correlation should look like. So this is a theoretical curve, and then they find points that lie on this curve, of course. But the important feature is that it has structure. It has this coherent oscillations structure on super horizon scales now. Yeah, so this L value here would be something like 200. And this negative peak here is between 50 and 200, I think. Yeah? So this negative peak here is what is exciting people. Whereas there's no such feature here. So this would be 100, I think. There's no such feature for the temperature. Yeah.
What does it mean for C to be negative?
Negative? Anti-correlation. So, yeah. So this is not possible for TT because it's an autocorrelation, but like TE. E can be positive and negative. Yeah. Okay. So the fact that you have a peak here also comes from coherence, and then the fact that it's at these low L values tells you that it's on super horizon scales. Yeah? So any alternative mechanism for explaining those fluctuations has to somehow be able to mimic that feature. And it looks if you don't have something like inflation, it looks acausal. Yeah? You're trying to do something which is on scales that are larger than the horizon at the time. Yeah? So it seems hard to do that at the
CLTE is a polarization correlation.
Yeah, it's a correlation between temperature and polarization, and a particular polarization mode, the E mode rather than the B mode. We did measure that. We also measured the EE autocorrelation. Yeah? And so this is the one qualitatively new feature that the TE actually tells you. Yeah? Otherwise, when you actually solve the inverse problem, both TT, TE, and EE, those three correlation functions, they're all dominated by scalar fluctuations. So at the end of the day, they all basically tell you about the same function. Yeah? So it's just they give you more statistical power, but they don't give you some dramatic, qualitatively different thing, except for the fact that polarization. Okay, there's another nice feature about polarization is that it's localized at the time when the CMB was created. Yeah? So typically, except for late time reionization of the universe, but if you ignore that. Polarization is only created by scattering from free electrons. Yeah? And after the CMB neutralized, the atoms became neutral, or hydrogen formed, and the CMB was released. After that time, there were no free electrons around. Yeah? So there wasn't any polarization created at late times, except for this, very late during reionization. Well, that's different for temperature. You can actually produce temperature fluctuations at late times. For example, there's extra fluctuations that are created when dark energy becomes dominant and things like this. So this most directly isolates the time of last scattering. Yeah, you're really seeing a snapshot of exactly at that time rather than some evolution afterwards. That can also be present here on large scales for TT. Yeah?
When you write down this condition, here you assume already that different modes don't couple.
So when I do what?
You assume that different modes don't couple. However, when you make this transfer function from the early universe up to now,
Good.
we know that
Good. When you go to, I showed to you that in linear theory, different K modes don't couple.
Yes.
So you can prove that just comes from translation invariance.
Yes.
Yeah? It's true that and for the CMB, that's good enough because the CMB is very linear at all times, yeah, and all scales. It's true that when I wrote down this guy, you have to be more careful because this is for now the density profile, and that can have on very small scales it becomes nonlinear. So here I should put a cut in K. If the K value is too large, then this linear relation would break down, and you have to do it full numerically. And that's why sometimes when you see plots of the power spectrum of density fluctuation, and I think it looks something like this, yeah, as a function of K. And again, it's not exactly flat or something, yeah, and that's because you have this transfer function that makes it change. And this change here comes at the scale corresponding to the horizon at matter radiation equality. And the problem appears, at very large K values, you can't trust your linear prediction for the power spectrum. So when you look at the data, actually, you will find that there's more clustering than the linear theory would predict on these very small scales. But then you can do numerical simulations, and you can account for this nonlinearity also and fit this better. Or you can do second-order perturbation theory. Then you would have this kind of mode couplings, and you have to worry about those things. Good. Yeah.
The statements that you're making about
Yeah.
TT being sourced primarily by scalar
Yeah.
predictions, does that remain true if you modify gravity, or is that fairly independent of?
Ooh, if you modify gravity.
So if you consider modified gravity, vector modes or tensor modes sourced?
Yeah, good point. I haven't looked at it too much, and I'm not aware of. I couldn't even point you up to. I would have to check. But presumably we could think of, yeah. Let's think about it afterwards. Maybe there's a simple way of seeing that it should or should not matter. But yeah. Well, let's see. Okay. It probably depends what you mean by modified gravity. I'm sure you could cook up something where it doesn't matter. But let's see, maybe in the cases that people have considered most where it matters there. We can check. Okay, so any questions on this? And now I want to move on to actually my lecture 4. This was partly lecture 3. So what I want to talk about today is in some sense open-ended. So I'm just going to talk and then stop at any time, because so from this point on, I told you the basic facts. This basic picture is, I think, what we should carry away and try and understand every aspect of it. And what I tell you now is like bonus. So, but it's stuff that is closer to what people are talking about these days when they do research. So the two things that I picked was non-Gaussianity and then hopefully you'll say a few words about UV sensitivity of inflation, which is something I've thought about for a while. And that's basically the question. It can be viewed as a problem or as an opportunity, for studying inflation. And I view it as an opportunity because usually, inflation hides high energy physics. Yeah? Like, for example, if you wanted to study monopoles or some relics of, gut scale physics, usually inflation makes sure that they are not observable. So it's a very efficient mechanism for actually, hiding very high energy scales from us. But there are theoretical aspects of inflation that are nevertheless sensitive to assumptions that we make about the theory at the very high scales, up to the Planck scale. So I want to hopefully talk about those. But let me start with non-Gaussianity. And so it relates directly to what we were talking about, these fluctuations that are produced here. So far we only calculated, this was painful enough, but we calculated the power spectrum or a 2-point correlation function for these fluctuations. And that's all we need to calculate if the fluctuations were purely Gaussian. Yeah, so if fluctuations are drawn from a Gaussian distribution, then you know that the 2-point function describes the whole statistics. Yeah? Any higher order correlation function, if it's odd, it vanishes identically, or if it's even, it can actually be re-expressed in terms of the 2-point function. Yeah? So this would be the full answer if the fluctuations are Gaussian. And slow roll inflation, in fact, predicts that the fluctuation should be very nearly Gaussian. And the reason is that any non-Gaussianity is basically a measure of interactions of the inflaton field. Yeah? So what we did in order to calculate the 2-point function was we calculated the second order expansion of the action in terms of, let me just give it. This takes a while and 1 Maldacena to get, yeah. But at the end it boils down to to a simple action like this. And so this is the free field action for this field R, yeah. So free field. So in order to get into study interactions, I would have to actually go to third order. And study couplings of the sort R dot square R, grad R squared R, and things like this. And it's considerably more painful to then to go to this step. Yeah? So, but at this point there were no interactions. And so these are the first non-trivial interactions. And so for slow roll inflation, and actually, so when you compute this, you find that this is proportional to the first slow roll parameter squared, whereas this one is only proportional to 1 power of the slow roll parameter, so it's suppressed by slow roll. And that qualitatively tells you that the inflaton field is very weakly coupled. Yeah? So in slow roll inflation, in order for inflation to happen, you had a very flat potential. So the self-interactions of the inflaton are weak. And in fact, where most of these interactions are actually coming from is not from interactions of the field itself, not from V of phi, but from the Einstein action. So those are purely gravitational interactions that have to be present also. But those are also small. So those are the ones that Maldacena computed and showed that they're suppressed by slow roll. Yeah? So for slow roll inflation, you actually expect that the field is very weakly interacting in order to have inflation in the first place. Gravitational interactions are small, basically Planck suppressed. So you don't expect, that there should be significant non-Gaussian higher order correlations. But that also makes it a good test. Actually, I'm going to show you a theorem today that allows you with one sweep to rule out all kinds of single field inflation models. And actually, that test goes beyond slow roll. Yeah? So there's a very powerful theorem, again going back to this guy. Okay, so let me define how do we define non-Gaussianity? So from this third order action, you can compute the 3-point function, or in Fourier space, it's called the bispectrum. And so it's defined just like we defined the power spectrum, but now just you have 3 entries here. And so there's a delta function. And then here this function, which is called the bispectrum, that depends on all 3 momenta. Yeah? So now I'm looking at the correlation between 3 different modes with 3 different wave numbers. Yeah? The wave numbers are constrained to satisfy this momentum conservation, the delta function basically. So that also appears for the power spectrum. And then you have this bispectrum, which now depends on the magnitude of all 3 of these wave numbers. Yeah? But this momentum dependence actually makes this a very, very powerful probe of high energy physics. Yeah? Because for the power spectrum, if you remember, we were only measuring dependence on one momentum, whereas here you have a whole function, a whole higher dimensional parameter space of momentum dependence that you can exploit. Yeah? So this momentum dependence reveals a lot. UV physics, maybe. And in particular, different mechanisms for laying down these primordial fluctuations. So you can certainly consider things that aren't single field slow roll models. And all those different mechanisms typically, have characteristic signatures that in this bispectrum function. Okay, and but there's one constraint on the momentum dependence, that because of this delta function, these momenta have to form closed triangles. Yeah? So that therefore the signatures of different models of inflation or different mechanisms for producing fluctuations are then often expressed in terms of at which kind of triangle configuration the signal peaks. Yeah? So typically you produce power for all different kinds of shapes of triangles, anywhere in this momentum space that is constrained by this. But for different models for certain types of triangles produce a peak in the signal. It's not a uniform function typically. So there are 3 important triangles that people have considered. So the first triangle is called squeezed. And that's when one momentum mode is much less than the other 2. Yeah, so the triangle will look something like this. And so if one of those momenta is very small, then the other two have to be nearly equal, of course, to close the triangle. And so that's the shape that actually arises, for example, in single field slow roll. But as I argued, and I'm going to show you, but the amplitude is small. So the signal is small everywhere in momentum space, but it nevertheless peaks at this particular triangular configuration. But it's so small that you can never see it no matter what kind of triangular configuration you test. And it also arises in multi-field models. And in that case, it could be large. Because when you have more than two fields, then one field is constrained to be weakly coupled because it's the one that drives inflation. But the second field, isn't constrained that way. And so you can actually produce fluctuations in that second field that have larger non-Gaussianity than the fluctuations in the inflaton field itself. And so then there are different ways of converting those fluctuations into fluctuations that we observe. And depending on how you do that, you may or may not produce large non-Gaussianity. Okay, a different shape is equilateral. When all the momenta are equal. And this arises when you add higher derivative interactions to your action. So higher derivative. And so those are models like dBi inflation, ghost inflation, models with general speed of sound. So in a moment, I'm going to show you some of these models more explicitly. So they're very distinct from these type of models, where you don't have non-trivial corrections to your kinetic term, basically, in the sense that they produce non-Gaussianity with this particular shape rather than this shape. And then finally, a third shape is called folded. Where the triangle looks something like this. And that one has been introduced only pretty recently, actually, last year, I think. For a long time, these two were the major kind of shapes that people looked at. And so this folded shape arises when you look at excited initial states. So if inflation started in an excited state rather than in its Bunch-Davis vacuum state that we basically assumed when we did our calculation or tried to justify, then you can see some remnant non-Gaussianity from this excited state. Yeah. Yeah.
Maybe those triangles on the flat.
Sorry, there.
They're in a flat. You guys account for curvature.
Sorry, curvature. We're now in Fourier space, so I'm just.
So is this Fourier space of the sky?
Yeah. I mean, the 3-point function is also 3 points in a real space on the sky that you compare. And then you do the Fourier transform of that 3-point function, and you get triangles in Fourier space. So sometimes you see that people draw these triangles on the CMB map, and then they label them with Ks. But of course, the CMB map is real space, and the Ks are Fourier space. So it's a little bit of a fake, but you do the Fourier transform in your head, and so Fourier transform and squared in your head. Okay. Yeah.
If I have a curved space and then I do a Fourier transform, do I get curvature in my Fourier space?
Well, I'm doing a Fourier transform of functions of x. I'm not sure where even metric or curvature comes in. No, I'm doing the Fourier transform of these guys. So this R here is in real space. It's just a perturbation in x, 3-dimensional. At different points in space have different values of this curvature locally. And I'm just defining the Fourier transform. Three-dimensional, yeah? This Fourier transform assumes that you have a flat background. That's true. A globally flat universe. Okay, I see what you're saying now. So yeah, you would have different. You could have different functions if it's non-flat.
If we're doing a 3D Fourier transform, but all we have is an image. We have a 2D image.
Yeah.
So how do we extract 3D information?
Sorry, but in the 3D image, I'm comparing 3 points.
Right.
Yeah, and the 3-point correlations between like 1 point and 3 points on the sky, in the sky.
Sure. Okay. So the momenta are two-dimensional.
Yeah. So you can actually. So one test would be. Sorry, the momenta are? No. The momenta are 3-dimensional. Sorry. So the sky, again, we have this transfer function. You have this P of k, which is a 3-dimensional power spectrum. And one part of the transfer function is this projection effect that you want to project it onto a 2-dimensional sky. And then you get the angular power spectrum, the CLs, which are spherical harmonics, 2-dimensional spherical harmonics. Yeah? So you do the spherical harmonic transform of the 3-dimensional Fourier transform. Yeah? So that makes it from 3 to 2. It's true. When people then at the sky, again, this thing would have to be related to the CMB by a transfer function. And then you get the angular by a spectrum, not the 3-dimensional, this Fourier one. And effectively, this angular by spectrum is just, taking the correlation of three ALMs. Okay? You take ALMs from your spherical harmonic decomposition, and you compute the correlation between 3 of them. Okay, any questions on this?
I'm not sure what this folded configuration means for the, like, our K1, K2, K3 for folded.
For folded? So K2 and K3 are equal, and they're both equal to twice a half K1. So maybe, yeah, let me write it out. So this was this. Here they're all equal. And here K1 is twice K2, twice K3. Yeah? And of course you can have intermediate triangles, you can have, of course. But those are 3 triangles, and then you can have, you can have elongated and isosceles triangles, and that, yeah. But it just turns out that most of the models actually peak in those kind of simple configurations rather than something intermediate, or having a broad distribution of the signal.
So to find non-Gaussian, do you assume that there is a minimum, is a maximum number of equals?
Yeah, you mean for this excited state? Yeah, this is what I wanted to say actually before I stop. So these two here would be slightly more generic than this one, because if you start with an excited state and you just add a little bit of e-folds before you get to the time when CMB scales were created, yeah. So imagine inflation lasted for a total of 80 e-folds. So your initial state is set at the 80 e-fold mark. CMB scales were created, between 60 and 40 or something like this. And so there are 20 e-folds extra, where the excited state basically has time to relax, and it relaxes exponentially quickly. So what you really have to hope for is that inflation lasted for an absolute minimum number of e-folds. So if it just lasted 60 and maybe a few e-folds more, then you could see some remnant signature of that excited state. So it's very easy to hide this. You just add a few e-folds, 5 or 10, and this becomes very, very small. But it's a similar issue, for example, when you try to study tunneling in the landscape, for example. And people also have these arguments. Tunneling also always happens to a curved universe, an open universe actually. And so if inflation lasted for the minimal amount of e-folds, then that curvature wouldn't be removed completely. The flatness problem would just barely be solved. Yeah? And you could actually see some of that remnant curvature from the tunneling event. Yeah? But that's really what they're hoping for. They're then hoping for that only the minimal number of e-folds of inflation took place after the tunneling. If you add a little bit, then it's just the same issue as you have for this excited non-Gaussianity. Yeah? Okay. So this was the kind of information you can get out of the shape dependence. And so let me now also define what you mean by the amplitude of non-Gaussianity. So for the power spectrum, defining an amplitude was trivial. We just at some scale we ask what's the magnitude of the power. Here it's slightly harder because you have to tell me really at what's there's some ambiguity in your convention for how you define the actual amplitude of non-Gaussianity. And so the definition that I want to use is inspired by something, by like a simple ansatz that is called local non-Gaussianity, which if you imagine a redefinition of your curvature perturbation, a field redefinition in real space, where you say your curvature perturbation has a linear Gaussian part, and then some non-Gaussian, some nonlinear correction at some fixed point x. Yeah. And so this quadratic correction is multiplied by an amplitude FNL. Yeah? And we usually use this as the amplitude of non-Gaussianity. So if you take this ansatz, for example, and plug it into our formula for the bispectrum, yeah, so you do Fourier transforms first and things, then you get the following bispectrum. And these factors are annoying, but they're historical, so nothing I can do. And then two more such terms actually where you just cyclically permute these K1, K2, and K3 momenta. Yeah? So the bispectrum then reduces to a sum of just products of the power spectrum. Yeah? And you have this overall factor of FNL local. And so when people constrain non-Gaussianity and tell you one number, that's often the number that they tell you how big this value FNL is.
That's for each triangle.
Huh?
That's for each triangle.
No. So I'm actually going to prove to you that this will correspond to the signal peaking at a very particular triangle. Yeah. So this is here I haven't talked about triangle whatsoever. Yeah. So when I tell you the full, I don't have to talk about triangles when I tell you the full function, this full bispectrum function. Yeah. This function will have some value for different combinations of K1, K2, and K3. All I'm saying by these triangles that function will be maximal at a particular combination K1, K2, K3. Yeah? So we can ask for this particular shape. Yeah? This is one particular shape that arises when you make this ansatz. For this shape, where does the signal peak? Yeah? So let's prove that. What do I do with now? Yep.
So does this number this is a number or does it have K dependence?
With
FNL,
does
it have K dependence?
it can have K dependence, yeah. So here I'm not assuming K dependence, but it can.
It can depend on F.
Sorry? Well, let's say in this ansatz not. When I try to generalize this, you could assume some K dependence. That's then called running non-Gaussianity. And yeah, if I'm guessing Marilena's surprise talk correctly, he might be talking about something like this, but I'm not sure. By the way, there are two student talks that I can advertise. So she might be talking about non-Gaussianity, but I might be putting something into her mouth. And then there's also, I told you compute the third order action, and from the third order action, then you compute the bispectrum. Yeah? This is actually highly non-trivial. Yeah? It's much more complicated than for the two-point function, because now the vacuum is actually, you have to compute the interacting vacuum, it evolves in time, and all that stuff. Yeah? So what you have to do is you have to do something called in formalism. Yeah? As an alternative to computing regular scattering amplitudes where I compute in-out. Yeah? And so that was developed by Maldacena and then Weinberg. And so this evening, I guess, I can't pronounce the second name, so this evening I think Peter is going to talk about extensions to this in formalism. So if you really want to know how to compute bispectrum from this, you have to bug Peter tonight. Okay, what did I want to do? Okay, so I wanted to prove what kind of shape this thing peaks at. Yeah? So if you assume that the power spectrum, if this power spectrum here is scale invariant, so scale invariant means that it scales like k to the minus 3. Yeah? So we had this other definition of the power spectrum where we had an extra k cubed, and if that power spectrum was exactly constant, that's what we mean by scale invariant. N is equal to 1. So this p that I have defined here would then scale as k to the minus 3. Okay. So if I input a scale invariant power spectrum into here, for the first term I would get 1 over k1, k2 cubed. Yeah? And then I also get a 1 over k2, k3 cubed plus 1 over k1, k3, I guess, cubed. Yeah? And so without loss of generality, we can assume that, let's just order them and say k1, k3 is smaller than k2, smaller than k1, or equal. Yeah? It's just arbitrary ordering of the momenta. I can do that. And then if you look at this function, you will see that this function peaks in this configuration, when the smallest one is much smaller than the other two. Yeah? Because then you have one of these terms basically diverging and giving you a large value. Yeah? So this particular shape, this ansatz of local non-Gaussianity, something that is local in real space, would give you a squeezed triangle. Okay, and then so basically motivated, I think, by this ansatz, you can define a generalized amplitude for non-Gaussianity if you say that you define an FNL to be equal to this fact I haven't seen anywhere. I worked this out last night, so you should check this. Yeah. If you evaluate the bispectrum at the equilateral configuration when all the k's are equal, yeah, and divide it by the power spectrum at that same k squared, then that's one possible definition of the amplitude. And so that's what I want to use in the following. Yeah, so if you gave me a particular model that produces a bispectrum, you can compute that bispectrum at any combination of k1, k2, k3 as long as the momentum is conserved. If you arbitrarily choose to normalize it at this, at the combination when all of them are equal, you can define this amplitude like this. Yeah?
Doesn't that just give us the amplitude of the equilateral triangle?
Sorry?
Doesn't that just give us the
At the equilateral, yeah, but you're now doing it for an arbitrary shape. You're comparing all shapes at that point. I think that's what's happening. So you have to compare it somewhere, and this is just one way of doing it. The point is, we're normalizing it relative to the power spectrum squared. Yeah. So yeah, otherwise this would have been trivial. I could have just said, evaluate the bispectrum anywhere. Just tell me where you're evaluating it, and in all your models evaluate it at the same point. That would be a fine definition of the amplitude. Yeah? Here, I just want to normalize the amplitude by the power spectrum itself. Yeah? Because that's something that comes out when you make this ansatz here. Yeah? That is, the bispectrum is actually power spectrum squared in some sense. Yeah? Okay. So let me give you then current observations on this FNL parameter. So most constraints until recently were on this kind of ansatz. So they were constraining this FNL local parameter, or basically the squeezed triangles. And so they had the latest limits are something like -4 and 80, 95% confidence. Yeah. So let me explain to you what FNL of 100 basically means, because this FNL parameter is some number that you probably have no intuition for. But if you look at this ansatz, yeah, then we know it's this R Gaussian plus FNL R Gaussian squared. Okay. So the linear piece, and that's the dominant linear piece. And we know from measurements of the power spectrum that this R here is of order 10 to the minus 5. Okay. And so this linear piece also is of order 10 to the minus 5. So there's a factor of 10 to the minus 10 here then. and this is then the FNL that multiplies this 10 to the minus 10. So when you're measuring something or constraining something, FNL to be less than 100, yeah, corresponds to a constraint on non-Gaussianity that is 0.1%. Yeah? So we already know that the fluctuations are Gaussian to 0.1% accuracy. Yeah? And that's, by the way, that's better than the constraint that we have on curvature. In curvature, we had this 1% constraint on omega total, or the curvature of the universe. Yeah? This is better than that.
But that 0.1% is very dependent on this ansatz, right? You make other ansatz that are constrained to 1%.
I wouldn't think so. I mean, at this rough level where I'm just saying, it's 0.1% Gaussian, I think it's very, it's order of magnitude is not very dependent on the ansatz. Well, we're constraining a particular triangle here. It's true that when I read off this constraint, it could be that you have some crazy model that has a huge peak at some different triangle configuration, but is smaller than that triangle. So yeah, in that sense, it's true. So for example, if you had deep, actually, I'm gonna show you a proof that any single field model, not just slow roll, would actually predict you something like this. Yeah? Where in the squeezed limit, you actually have to have nearly vanishing 3-point function. Yeah? And let me tell you one more thing, and then I'll tell you this theorem. So the constraint on equilateral triangles is something like this. And so that constrains, for example, things like dBi inflation. Between what? So local is FNL corresponding to this ansatz, corresponding to this particular shape of bispectrum, which peaks at squeezed triangles. Yeah? And so very roughly, this local is not quite exactly the same as squeezed, but it's similar to squeezed. And then, as I told you, local would be the case relevant for single field slow roll, multi-field models. Yeah. So our prediction is that FNL local, from single field slow roll. Maybe I should say that. Our prediction. Actually, no. My next page. Okay. So let me tell you a little bit about what we expect theoretically for these different parameters. And so for some cases, the expectations are very clear. I mean, we even have theorems that you can prove. Yeah. And then for other cases, the expectations are still being worked out. So for example, as I told you, a single field slow roll predicts these squeezed triangles, and it predicts an FNL value for those configurations that is of order epsilon or eta, so it's of order 0.01 or smaller. Yeah. So this constraint that it's consistent with 0 is something that we would expect if inflation really happened by a single slowly rolling field. Okay, so now let me give you this theorem that I advertised. So it's called the single field consistency relation. So Maldacena proved this. Oh, I'm abused. Oh, whoa. Okay. So he proved for slow roll models, and then this was extended by Creminelli and Saldarriaga. They basically showed that it actually doesn't even depend on assuming slow roll. It's just something that if you assume a single field and almost nothing else, or really nothing else, this theorem would follow. So any action, any crazy kinetic terms, anything, but restricted to a single field. then in the squeezed limit where you say one of the momenta goes to 0 or is much smaller than the other two, this 3-point correlation goes to 1 minus ns, and then the product of the power spectra. And then delta function at 2 pi. Yeah? And so in particular, it's suppressed. This would then roughly be your FNL value. Yeah? It's suppressed by 1 minus ns. And for example, in the limit where you precisely scale invariant, this correlation vanishes. Yeah? No, K3. Yeah, because in this limit, K1 and K2 will be equal, and K3 will be the long wavelength mode. So effectively, the way then you prove this limit, so I sketched a proof in my notes. It's not perfect because I really did this very quickly. But so in this paper, they sketch it even more. It's 2 lines. And I thought, oh, cool, then I can show you because it's 2 lines. But then when you think about it, it's a little bit, it's 2 lines in their mind. Actually, 1 line in his mind. And in my mind, it would be like a page, I'll say. But actually, yeah, there's another paper, Chang et al. They prove it in 3 pages. They call it a formal proof of the end. And then they prove it in a whole page. Again, they prove it in a different way in 20 pages. So there are different ways of proving it, but the basic idea is that you have one mode that exits the horizon much earlier than the other 2 modes because the k value is small. So this small k corresponds to a very long wavelength mode. Yeah? So it will exit the horizon very early during inflation. Yeah? And after that, it freezes and it acts like a background for the other 2 modes. Yeah? So you could ask, so then what you do is you compare basically the power spectrum of the 2 short modes. Yeah? So these are both short wavelength. You can compute this power spectrum in the presence of this long wavelength background mode. And then ask how is it correlated to this long mode. Yeah, so compute this, basically the correlation between the long mode and the power spectrum of these 2 short modes. And you find that when it's scale invariant, there shouldn't be any correlation. Yeah? These 2 short modes couldn't care less if there's a long wavelength background. So that's the basic idea. And, you just for this you can write a Taylor linear expansion in terms of perturbations induced by this long wavelength mode, and then you prove this. Yeah? And in Fourier space you will get this answer. But it's powerful because it literally assumes they're very clear. The reason the proof is 2 lines, but the paper is 4 pages, is that in 4 pages they justify that they're assuming nothing, other than that it's a single field. Yeah? So what this means is if you see an FNL in that squeeze configuration, yeah, so if these error bars weren't like this, but you find some evidence for a positive value, and every blue moon, people claim evidence for a positive value. So if any of those claims hold up, then that means by this result, yeah, inflation couldn't have been a single field. Yeah? I mean, it's more powerful, and a particular example of this result is if you just compute it directly for slow roll. And then you will find this. You will find, for slow roll, you also find the suppression by 1 minus ns. But it's actually more general than that. Around and doing what? I mean, it depends. Yeah, it depends whether its fluctuations contribute to the fluctuations that we observe as curvature perturbations. Yeah. So what you're talking about are isocurvature fluctuations in the second mode, and what we actually observe are these adiabatic fluctuations in the curvature. It depends on how you convert those fluctuations into the second direction. So it can still hold, but this is basically a statement that there's only one clock during inflation. Yeah, one field that determines the time evolution. And if that's true, and that the fluctuations in that clock also determine when inflation ends, and that those are the fluctuations that you actually observe. If anything is, if you mess with that, this is not guaranteed to hold anymore.
So are these all from WMAP, all you found?
Yeah, these ones are. I think a W map, and you have to add little else. This is pretty much CMB only. Yeah, very much. So actually, yeah, I was about to say something else. So Planck, for example, will have error bars on this local guy. So 1 sigma FNL of order 5. Yeah, this would be Planck. And then this other guy, this CMB pole thing, is projected to have like an error bar of 2. And for example, some of the recent claims that claimed for detection of this FNL local. Yeah, so there was some 2 sigma detection hint that this was actually not 0, but some positive value. Their mean value was around 40. Yeah, FNL local 40, 50. So if that was really true, if it was 40 or 50, then Planck would detect this at 8 to 10 sigma or something like this. Yeah, whereas at the moment it's very marginal, 2.5 sigma, depending on how. So if it's true, you will know with this guy. But so there's an intrinsic problem that, yeah. Yeah. Okay. Good. You can tell me. There's a good reason why the constraints on positive FNL are stronger than on negative. Yeah? If you look at this parameterization, for example, so a positive FNL. Okay, we will have to be careful whether the sign here is right, because and it's not going to be my fault alone. So there is historically something that for a long time went unnoticed, that Maldacena sneaked in a different sign convention when he wrote his non-Gaussianity paper, and everybody became a big fan of that paper, and then we're using it for everything. But he was actually using the opposite sign convention from the convention that is used when you constrain the data. And it's important because the sign actually, as you see, these constraints are asymmetric. Yeah? And so let me not figure out whether the sign is right, but just tell you qualitatively why there's a difference. Yeah? So the difference is because a positive and a negative FNL means that you have more or less fluctuation at a given point. Yeah? If it's positive, say, you have a higher fluctuation, and if it's negative, you have lower fluctuations. And it's typically just easier to measure something there than some absence. Yeah? Measure a high density fluctuations than a void, an absence of a fluctuation. So that's roughly the idea. I think it's just easier. The problem I now have, I think this sign is right, but it goes in the opposite way of the way I want to describe it. And I think it has to do is because then when you go to CMB, yeah, hot and cold spot, it's easier to measure hot spots than cold spots, but a hot spot will correspond to the opposite in terms of the density fluctuation. So that's it. I think you have to do a double sign flip, and then you get it right. So trust the sign, and then figure it out for yourself that it's actually a lower density fluctuation, which corresponds to a higher CMB spot that we can measure more easily. All right? Okay. Okay, I wanted to say something about dBi inflation and higher derivative interactions. But if people are more interested about UV sensitivity of inflation, I can jump ahead. What do you want to hear about? UV sensitivity or higher? Actually, UV sensitivity. Because these higher derivative interactions are actually part of the UV sensitivity story. It's not so you can't just add high derivative interactions and you cross your fingers and think you're going to be fine in the UV. Typically, adding high derivative interactions, will cause you to think about the UV more carefully. Okay, so 3 examples that I want to talk about are called the eta problem, gravitational waves from inflation, and then also non-Gaussianity. Okay. So let me make some generic statements about effective field theory and inflation. So typically we can consider different energy scales. So inflation will happen at some scale, and one measure of this inflationary scale is the Hubble parameter. And we know it happens well below the Planck scale. Yeah? And that has to be true in order to satisfy normalization of the density perturbations, for example. And in fact, it has to happen below the God scale even. And so there can be, also can be a string scale somewhere, a Kaluza-Klein scale corresponding to the size of extra dimensions if you have them. There can be other particles. Yeah, and some our unknown theory of the desert between the TeV and the Planck scale. So typically, when we describe inflation, we do that in an effective field theory where we introduce a cutoff lambda that has to be below the lightest particle that we haven't accounted for. So we then imagine we're integrating out all these higher states that we're ignorant of, and we parameterize our ignorance by just adding higher dimension corrections suppressed by this cutoff scale to the inflationary action. So this is just a standard thing in effective field theory. So what this means is that there are often generic corrections to the inflaton potential of the form, some operator of dimension delta suppressed by m to the power delta minus 4. And so m is the lightest particle that has been integrated out with a mass above this cutoff lambda. So you can then ask, under what circumstances are these corrections dangerous for inflation? Yeah? And so remember, we defined these slow roll parameters for inflation, where you took m Planck squared over 2 v prime over v to be less than 1, and this eta parameter m Planck squared v double prime over v. Yeah? And so it turns out that this condition here, that this is less than 1, is sensitive to dimension 6 m Planck suppressed operators. So operators, corrections of the form v phi squared m Planck over m Planck. So if I choose my cutoff to be the Planck scale, yeah? And that's the absolute most conservative I could imagine. If in reality, for sure the cutoff is going to be somewhere below the Planck scale, yeah, because I have all these scales and I have to set my cutoff below that. But okay, assuming making this very strong and conservative assumption that there's nothing up to the Planck scale. But we know at the Planck scale something has to happen because graviton scattering becomes non-unitary. There's some degrees of freedom. Okay, so I put the cutoff here, and even in that case, you would think, normally in particle physics, if you have a Planck scale cutoff, Planck suppressed operators, are usually irrelevant and decouple from the low energy physics. For inflation, that's actually not true. Yeah? This condition here can be modified by order 1. Yeah? You can actually induce some order 1 corrections to the eta parameter by precisely such a Planck scale suppressed operator. Yeah?
Does that make an assumption about
H at the time of inflation? Well, you see, I sneaked in here. When I said dimension 6, I constructed this dimension 6 by just having, phi squared giving me 2 dimensions, and then an overall mass, an overall scale, which was the inflationary potential. And that's that's like a Wilsonian genericity argument. There are no other scales in the problem other than H, and so the mass of the inflaton would be H, and that's in some sense in that generic situation.
Eta B is very UV sensitive, right? So in other words, eta is very UV sensitive, right?
Yeah, exactly.
So if I had, say, supersymmetry or anything like that, everything would be really different.
So okay, supersymmetry. So it's interesting whether supersymmetry would help you. So you need something to help you because generically, from the effective field theory point of view, any kind of correction to eta, typically smells dangerous if you add them with order 1 corrections, order 1 coefficients. And so the problem with supersymmetry doesn't actually cure the problem, is that it's automatically broken during inflation. You have a positive, yeah. So the splitting of supermultiplets is at least h. So supersymmetry doesn't help you to reduce eta below 1 because you break it by inflation itself, and more likely you break it at higher scales even. Other things like shift symmetries can help you. Yeah? If you have an axion field, for example, an axion would forbid this term because it has a symmetry where phi goes to phi plus a constant. So if the inflaton field, so one of the most attractive inflationary models, but it doesn't quite work when you try to do it in string theory, is called natural inflation.
How generic is that statement?
Which statement?
Like the statement that for slower, we can phrase this could we phrase this generically as saying that the parameters which are crucial for inflation, slow roll inflation of any kind, are very UV sensitive?
Yeah.
Is that general?
I think so. Yeah, in an effective field theory, in a Wilsonian sense. Yeah. But okay, now I'm going to show you one way around this. So in natural inflation, you impose a symmetry. Phi goes to phi plus a constant. And so an example for such a field would be an axion field. And if that's the case, then you have an inflaton potential, non-perturbably generated, that looks something like phi over f, where this f here is the axion decay constant. Yeah? And if you do the slow roll analysis that we did in the first lecture for this kind of potential, you will find that it gives you a slow roll if this f here is bigger than m Planck. Yeah? But okay, fine. So if this decay constant is bigger than m Planck, then this potential gives you a slow roll. But corrections to the potential, these delta V corrections that we worry about, are constrained by the fact that the action has to respect the shift symmetry. So you won't actually be generating these kind of terms for such a field. Yeah.
If greater than m Planck usually is a problem in string theory.
Exactly. That's what I'm going to tell you next. Yeah. This is not string theory. This is just natural inflation at the time, 1996, by Fries and some other people. This is just if I'm not telling you really what my field phi is, but I'm telling you it has a shift symmetry, so something like an axion, and then I'm just telling you the requirement is that f is bigger than m Planck. So now you look at string theory and you see there are hundreds of these axion fields, very generically. Yeah? So you hope, sure, one of them will actually do the job. And so in the notes I show you a schematic proof that this is not, that in string theory you always get f less than m Planck. Yeah, and this was proven properly by Witten and Peter Swertzik. I'm not going to get his name right. Ooh, whoa. Yeah. I know him actually, but I'm sorry. Okay, yeah, by Witten and Peter. So they looked at it in a host of axion fields, different types of axions in string theory, and they could show that there's always a problem that arises when you're trying to push the axion decay constant above the Planck mass. Yeah? But in principle, this would be one of the nicest inflationary models because it has a reason why the potential is flat. Yeah? Whereas often in many other models, there's no such reason, and you're always facing this eta problem, and often it's just assumed, okay, you can have accidental cancellation, of course, for a small range in phi values. So that, okay, there are all these corrections, but, you're just then saying you have more than one, they come with opposite signs, and accidentally for some small region of parameter space and small region in phi, in field space, they will cancel. But it's not as nice as having something like this. Okay, so this problem is even bigger. This is a problem that any inflationary model has that wants to give you 60 e-folds, because for 60 e-folds you need eta to be less than 1. Or I should say any model that looks like slow roll. Yeah? So, but then when you have models that produce large gravity waves, we showed last time Now this means that there's a distance in field space that the inflaton travels that is related to this tensor to scalar ratio in the following way. So if this tensor to scalar ratio is large, and if it's large enough for us to see, that means that this this distance in field space was much bigger than the Planck scale. Yeah? And what happens in that case is that you don't just worry about this dimension 6 guy, but you worry about an infinite series of higher dimension operators that all become relevant, because they're all suppressed by the Planck scale and have some powers of the field at top. Yeah? So they all simultaneously become important. Yeah? So you can write an infinite series here, of phi over m Planck to some power n. And the question really is, how does that series sum to something finite? Yeah.
Can't that do that and ruin the shift symmetry?
Huh? Exactly. So again, this is the best example where this is again okay. Yeah?
But if that sum is now...
No, these terms would also be forbidden by the shift symmetry.
What if it's a cosine?
Sorry? If it adds to a cosine, you say?
If the sum's to a cosine.
Then good. No? Oh, sorry. Yeah. No. This is a shift symmetry that is there in the absence of the inflaton potential. It's weakly broken by the inflaton potential itself. So, for example, if you have a shift symmetry, and not just this one. This is just specific to axions because they produce this cosine non-perturbatively. Yeah? But I could also do m squared phi squared inflation. Yeah? Simplest thing. Of course, this phi squared here also breaks the shift symmetry. Yeah? But if this is the only thing breaking the shift symmetry, and you arrange this with a small mass parameter, then it's technically natural for this parameter to be small, because any further corrections are constrained both by the shift symmetry and by the fact that this parameter here is small. So all corrections that you then compute, like quantum loops and things like this, will always be suppressed by mass over m Planck squared. And last time I showed you this has to be 10 to the minus 6, so this correction here would be 10 to the minus 12 or something. Yeah? So it then becomes technically natural. So you start with a shift symmetry, inflation breaks the shift symmetry weakly, and further corrections are constrained by the shift symmetry and this small parameter. Yeah.
One thing, I just want to make sure I get the kind of take-home message here. This doesn't mean that if we detect this ratio of R to such that this ratio is bigger than much bigger than 1, we have a problem because naively that would be generated by non-perturbative gravity.
So you mean these corrections will be generated by? Well, I'm not even talking about whether those are. Those don't even have to be gravity corrections. Yeah, I mean it's just that then you have to somehow have to explain to me why these. Here I'm actually being conservative by saying it's Planck suppressed. It's corrections that come about because I'm integrating out stuff at or above the Planck scale. Really, if I'm integrating out stuff that is below the Planck scale, this problem gets even worse. So I'm not even. This looks very quantum gravity likey because I'm sneaking in here this Planck scale. But the only reason I put it in the Planck scale is to to be as conservative as possible for this. I mean, you could put the supersymmetry breaking scale in there, Kaluza-Klein scale, something else. For specific models, you would typically find that this is violated much stronger than what we were assuming here. Yeah? Okay. So I would have mentioned, let me just point you to two references and then stop here. Just so that you don't think it's all gloomy at the end of the day. So this is what Witten and Swartzek found. But then last year, so mainly a paper by Eva Silverstein and also Alexander Westphal, Liam McAllister, and then previously a paper by Kashru and Dimopoulos and other people. So they came up with a model called axion monodromy. And this here is inflation. And both of these models have clever tricks of arranging that the effective the effective axion decay constant is actually bigger than the Planck scale. Yeah? So the simplest to understand is this inflation. What happens in inflation, you imagine in string theory you don't just have one axiom, but you have many of them, maybe hundreds. And so if you add hundreds of these fields together, you can get one effective field that has a decay constant that is enhanced by square root of n, square root of the number of fields. So they prove that this, for each one individually, you only have small values for this decay constant, but you can try and enhance them by the number of axion fields. And then here, this is another clever geometrical trick of when you wrap branes around certain cycles, you can extend the range of the axion decay constant. So if you're interested about those, you should actually either look them up or we can talk about those afterwards. And okay, let me stop here and not talk about Nagasaki. Thanks.